Hello everyone, welcome to this WEkEO training on natural disasters. My name is Alexandre Morin and I will be your trainer for this Jupyter Notebook exercise. So today's topic, as I've mentioned, is natural disasters, and more particularly we'll be studying in this notebook the Boris storm, which happened in September 2024. So we'll learn a few things in this notebook. First, we'll learn how to use the Harmonized Data Access API from WEkEO to access large-scale datasets, namely precipitation and flood indicators in our case. We'll use XRA and pandas to manipulate netcdf files, which is a common format in the scientific community in Python and programming. And we'll see how to track the spatiotemporal propagation of a flood wave, and we'll create various maps and animation to monitor this disaster. So natural disasters can encapsulate several phenomena, for instance wildfires, hurricanes or catastrophic floods, and those are obviously very significant threats to human life and also infrastructures and also ecosystems. And with climate change and global warming, it is very likely that such events will become more frequent and more intense in the future. And so this will have dramatic consequences on human activities, human lives, and of course the environment. And so this is why it is essential to leverage tools and models and observations in order to better understand how those events happen and how they work, and in that way we can enhance and improve future predictive models. And so on our particular case here, so we're in September 2024, where the Central Europe was hit by Storm Boris, which triggered one of the most devastating floodings of the 21st century in this area. So we know that the consequences were catastrophic, especially, for instance, within the Oder River basin. The Oder is a river that goes through Poland, mostly, and there was so much water that the infrastructure couldn't handle it, and we had record-breaking river levels in this region. So in this notebook, we'll try to monitor the water journey of this flood over the Oder River basin. So now in the next section we will set up the Python environment that we're going to work in for this exercise. So as mentioned here, we'll mainly retrieve data from ERA 5 and from the Global Flood Awareness System that are available in the WEkEO catalog, and that way we will reconstruct the event timeline with scientific precision. So as for the Python modules that we're going to use in this notebook, so if you already worked with Python, you are probably already familiar with some of the libraries, that we are using here. You probably already know NumPy, which is a fundamental package for scientific computing in Python, especially when working with arrays. So it's probably used in any Python project that exists. XRA is a very common library when you're working with netcdf files, which is one of the most standard formats for scientific data, which will be the case for our datasets that we're going to use. Matplotlib and CartoPy are used to draw and plot different graphs and maps in order to visualize the data. GeoPandas is used to work with geometric data, and Rasterio is used to study rasters data. It's especially useful when working with scientific imagery. So I think we can now start working on this. One thing I have to precise first is that if you are working within the WEkEO Jupyter Hub, make sure that the WEkEO Lab environment is selected here, clicking on the right hand corner of the window, because this environment has all those libraries pre-installed, so you won't have to install anything, and importing those libraries will work on the first try. So our Python environment is ready. Now I will do a little section about the WEkEO Harmonized Data Access API, which is a tool that enables us to retrieve data within the notebook. So from this notebook, we can access any product from the WEkEO data catalog using the Harmonized Data Access adapter. And as we are working on WEkEO Jupyter Hub, this client, this library is already installed. So in order to use it, we need to create a file called .hdrc in our home directory in WEkEO. So this file should contain our WEkEO credentials, and once it's created, we can access the dataset from the catalog anytime. So in the next cell, this next cell, so it allows us to create this particular file if it doesn't already exist in our home directory. And finally, it provides us with a WEkEO token to access the data. And if you don't already have it, I do actually here. This will ask you your username and password. So make sure you have a WEkEO account, but if you're already on Jupyter Hub, you should already have one. Okay, so now we are ready to download data. The question is, what data are we going to download? And for our first product, we are going to download precipitation data from the Area 5 catalog, which is so also available on the WEkEO platform. So Area 5 is, we can say, the gold standard for climate datasets, which is produced by the European Center for Medium-Range Weather Forecasts. So it provides a lot of climate data, a lot of variables such as temperature, precipitation, and other atmospheric variables. And so Area 5 is a combination of model data with observation assimilations. So this allows us to have very precise reconstitution of past weather, and this is what we're going to use here. So we're retrieving the total precipitation variable from this product. So this is the ID of the WEkEO product here. You can see here, so the complete name of the product on the WEkEO page is Area 5 post-process daily statistics on single level from 1940 to present. You have here some additional information on the dataset, and you can of course visit the dedicated page on the Copernicus Climate Data Store if you want to have even more information about the products. So this can be useful if you want to have to do deeper analysis for the exercises, for instance. So we have a spatial resolution of 0.25 degrees, so this is about 25 kilometers. We have, so the dataset that we are retrieving has a daily temporal resolution. So we have the total precipitation for each day in our time period, and it covers so from 1940 to present. But of course, we are only going to retrieve a few months of data. So we have so files that have a manageable size. Okay, so we will see now, thanks to the product, how many millimeters of rain have fallen over Central Europe in September 2024. So now here is the procedure to actually download the product using the Harmonized Data Access API from WEkEO. So here are the few steps that are required to perform that. So first you need to activate so Harmonized Data Access client. And then you have to write a data request for this particular product that I have introduced you. And to do this, you need to write a .json file that, for instance, I can show an example for you here in the data directory. So this file should be available to you in the tutorial package. And if I open it with editor, you can see that I have several items that I have written to retrieve the data. So here is the ID of the product that I've just shown you, and here are some additional requirements. So you can see that I'm requesting the precipitation variable from the year 2024, the month of September, which is when the storm happened. I'm retrieving all the days of this month, so the entire month of September, over this area, which is centered around the outer basin, etc. But if you don't know what to write, how do you write such requests? It's actually quite simple. So as explained here, in order to write this query, you can go to the WEkEO data viewer, so the page that I've just opened thanks to the link in the notebook, and select the dataset and click here on the download icon. Oh, I need to reconnect. Doing this quickly. And you can see here, when I click on the download, I will have all those items that I've shown you in the JSON file that I can select. So here I can select the total precipitation. Okay, year. Well, for the sake of the example, we'll just select a random year. It's not important right now. So let's say I want April 1980. I can probably do a select all here, yes. So for precipitation, you usually use daily sum because the amount of rain accumulates, of course, over time, etc., etc. You don't need to fill in anything if it doesn't have a red star, but what's important to notice here is that in the end you have a show API request button here, and this will immediately convert your specifications here into the proper format for the How.Data API, and you just need to copy it and paste it in your JSON file. So this is exactly what I've done to build this request. Then you can open your query here. So this is what I had in the file printed in this section, and then you can launch the search to find the files that you have requested. Oops, sorry, just corrected the variable name to remove an error that I had. So yes, now launching this search here, you can see that I have found indeed a file here, which is an NetCDF format, and finally you can launch the download of the file. So this shouldn't take this. The time it takes depends on the dataset and how well the WEkEO platform can access the corresponding catalog. But here you just need to wait a little bit to have access to the data. Okay, so you can see here that the file has been downloaded. You have some feedback here in the console. So now we have downloaded it, we are ready to explore the file. So you can see that in your package, in the data directory, you can see that this file here is present. You can see it here. And now using XLR, you can open it and see what's inside. So here we have a dataset with 3 dimensions. So we have latitude and longitude, of course. It's a precipitation dataset, so it covers a certain area like a map. And we also have a time coordinate here called valid time, which we can see here if we click on this icon to have some samples. Covers the 1st of September 2024 to the 30th of September 2024. So this is exactly what we had requested. And finally we have a TP variable here. If you want to know more about this variable, you can click on this icon here, which will display the metadata of the variable. And we have some, well, quite a lot of other items here to have more precision. So we can see that the actual name is total precipitation, so TP, this makes sense. It's in meters. And we have some more metadata here that we don't necessarily need to investigate right now. But what's most important is especially the unit of the variable, and we'll make sure of what it is, so long name and or description. And finally, in this netcdf file, we have some more global metadata here. So here we have some information on the provider of the data, on the convention that the dataset is following, and so on. Before we do any analysis, we can do some quick pre-processing of the dataset so it is more suitable for the Python manipulations. If we look at the latitude coordinate here, we can see that it goes in a decreasing order from about 60 to 34, 45 degrees north. It's usually not very practical in Python to manipulate datasets that have latitudes sorted like this. We want them in increasing order, so using the sort by function of xarray, we are just going to resort the latitude coordinate, so it is now in increasing order, as you can see here. So first we're going to just look at the storm and try to find it using this precipitation dataset. So first let's just visualize on the map what is our area of interest. So we're defining it here using so a long lat box, and we can just draw a quick map using a basic geographical features, so coastlines, borders, and coloring the land distinct from the sea. And so as you can see here, this is our box that will be our area of interest, so most of our analysis will cover this area in the red box. So you can use this extend variable to slice our data sets and have our precipitation focused on the Boris area. So Boris being the name of the storm, of course. So you can, and now what we want to do to look at the precipitation is to look at the time series of the precipitation and see when we have a spike in precipitation, which will indicate us the actual date of the storm in September. So to do that, we have to compute the time series. So first you can see here that I've selected using the cell method the dataset only within this red box. And now what I want to do is to look at the time series. So to compute it, you have to perform the average over the spatial dimensions, so latitude and longitude. This will yield, as you can see here, a new dataset that only has a time dimension. And so here we have the evolution of the average precipitations over the area covered by the red box. So usually we represent precipitation time series using bar charts with 1 bar per day, because we have daily data. So here you can use the the bar function from matplotlib. And here is the result. So you can see that we have plotted the total precipitation data multiplied by 1000, because it's very common to display precipitation data in millimeters. Here we have the time axis, and here we have our precipitation axis in millimeter, as I've mentioned. And we can see that around the 13th of September we have our maximum precipitation in this area, which goes up to 25 millimeters, which is a very, very high amount of rain, especially over such a large area. So yes, we have a very sudden here dry to extreme transition, we have some a little spike here, but here we have in from the 13th of September to the 15th of September or 16th of September, a period of extremely strong rain. And this massive surge is probably the Boris storm, actually, and it's probably what triggers well, the flooding that we have witnessed. So we can do something more now, which is to animate the precipitation data over the entire month of September. So this will give us some sort of weather forecast-like view of the storm. So to do that, we will just plot the entire dataset with one map per day. So we initiate it here. So this is the precipitation on the 14th of September. So this is just a static map for now, and we can see that we have a very strong here spot of very heavy rain, so more than 40 millimeters. In usual extreme climate indicators, a day with 20 millimeters is already considered very heavy, so 40 is quite extreme. And as I've mentioned, we want to have this but animated over the entire month. So here it's only one day, but we want to plot the same map over the entire month to see how this to see the trajectory of the storm. And we do this using the pcolor mesh function to draw each map, and using the update to repeat this operation over the entire month. And after a few seconds, this will allow us to see the Boris storm over the entirety of Europe. Alright, so you can see here that we are on the 1st of September, and if I click play, you can see here the very big spots of heavy rain, of extreme rain even, I would say. So if you're working on the book yourself, you can click on the slider here and just focus on this. Yes, 12th, 13th or 14th of September. This is the very heavy part. And then it dissipates, and we have, yes, much less rain in the area. But we can notice that for a few days here, the storm was kind of trapped over this area. And this being stationary, we can of course imagine how the total precipitation over those few days was extreme. So yes, in accumulation, we did have a lot of water falling down on this area, so no wonder that the flood happened over the river basin. But now we're going to use some flooding indicators to see how the Oder River responded to this extreme precipitation. So this time we'll use data from the Global Full Flood Awareness System, which consists in several indicators, and it is actually also based on RF5 data. So we'll use a soil water index indicator, which tells us how much the soil is filled with water, so how thirsty is it, or how dry is it, how dry it is, sorry. And so with this indicator we can see the behavior of the soil as a sponge, basically. We also use a surface runoff variable. So this variable quantifies the flow of water over the surface of the land. So, and finally we also have a river discharge variable. which is well, as indicates, so it indicates how runoff has filled the basin and the arteries of the Oder. And this quantifies the quantity of water that travels within the river. So all those variables are contained within a single product, which is called river discharge and related historical data from the global flood awareness system. So just like before, you can visit the dedicated WEkEO page to know more about the data. So here are our 3 actual variable names. We also have daily data, and those have a 5 kilometer resolution approximately. And we also have a very wide temporal coverage, but same as before, we are only going to retrieve data from 2024. So just like before, we're going to use data requests written from the WEkEO data viewer. So they should be already available here. So I've written 1 request per variable. We could directly do the 3 variables in a single request, but to ensure that the downloading is a success, I've just separated these. I've just separated the requests to have just 3 small requests. This is more secure in terms of network and downloading. And you can see that we still have well, the different items because it's a different product. So you should be able to build this request using the data viewer, but you can of course use them as it is now. So I already have the files available here in my directory, so I will not run the requests once again, but by executing the 3 following cells, you will see that you can download the product. So here you can see that I have interrupted the downloading myself, so I could still work on this notebook because I already had the data available. So let's open the 3 files here. So we have 1 dataset for the soil water index, 1 dataset for the river discharge, and 1 dataset for the surface runoff. And we'll start with the soil water index data. So what's interesting to see here is to look at how dry the soil was before the storm and what the state is after the storm. So in this section we will compute the soil water index anomaly. So usually when computing an anomaly, it's the deviation from a reference period. So we were not able to download 20 years of data, which we should normally do when working with climate data. So for anomaly, we will compute our reference period will simply be the entire year of 2024. So which we will subtract to well, the different dates that we want to study. So here, just to show you, our raw dataset covers the entire year of 2024. We have 366 days of data. So from 1st of January 2024 to the beginning of, well, 1st of January 2025. A little offset here. So it's not a problem. And we have our soil water index indicator that you can also examine in more detail. And so if we compute the average over the entire dataset, we have the average over the entire year of 2024, which we can subtract to the dataset to have an anomaly in percent. And this is what we have here now. And now we can plot 2 maps side by side. So one map of the soil water index anomaly before the storm. So here I've chosen the 10th of September. And then immediately after the storm. So here the 18th of September. So we can select each date using the cell method. And then those lines here are just used to set up and draw the 2 maps side by side now. And so we can see here that before the storm we had apparently a very high deficit in water in the soil, and that after, so we are still dry sometimes, but you can see here that we have some excess in water in this area in Czech Republic. But so we can see that shortly before the storm, the soil was exceptionally dry with regards to the 24 average. And then this part of the basin shifted to a positive anomaly. You can see here with a few percent of excess. And so this has very many possible interpretations, but we can see that the story is probably that the rain that was so violent that the soil, which was exceptionally dry, didn't have much time to store the excess water that was on the surface, which usually happens when the soil is too dry. It loses its retaining capacity. And this is probably exactly why the river levels peak so dangerously, because the water didn't have any time to be absorbed by the soil. So now we can use the three datasets to reconstruct the timeline of the storm and see how the different variables react with one another. So we are going to plot the three time series, well, four if we add the precipitation, of the variables over the area. So we will compute we'll compute the time series for the three for the three variables. So here you can see that for each runoff, discharge, and soil water index, I'm performing also a spatial average over latitude and longitude in September 2024. And if I plot all the curves, so here we have the precipitation that we have that we already know, that we already seen before, just as a line plot instead of a bar plot. Here we have the soil water index, here we have the surface runoff, and here we have the river discharge. And so we can clearly see the domino effect of the storm. So first, of course, we have the extreme precipitation here that lead with some sort of delay here the soil water index to surge here. So we have the peak here of precipitation in the during the 13th of September, but the peak of the soil water index is 4 days later, which is a lot. But in the meantime, we can see that the peak surface runoff is before the soil water index has absorbed all it can, because the peak here is probably around the 15th of September in surface runoff. So this is why you can see that indeed there was a lot of water running over the surface before it could be absorbed here by the soil. And finally, we can see that the river discharge is the variable that responds with the longest lag, because it represents time needed for every drop of water on the surface to reach the rivers and converge to the main river arteries. And yes, this culminated in the massive flood we've seen around September, the 18th of September. So here are a few exercises that you can do to complete this analysis. So one thing you can do is to plot the same curves but over the entire year of 2024. Remember that we have this data in our product that we have downloaded, and maybe you can see how exceptionally high those variables were in this area, even with regards to the entire year. And one thing you can do from those data sets is to identify the flood propagation using those time series. Basically, what you can do is that instead of looking at time series over the entire average over the entire area, you can look at the time series over two specific points, one upstream and one downstream of the other river, and see if there is a lag between the 2 points in terms of river discharge, runoff, but especially river discharge. And you can see, well, you can quantify the lag in days here between the two specific points to see how fast the flood has propagated itself over the Oder River. So now that we have reconstructed the timeline, we can wrap up this analysis by creating a dual animation of surface runoff and river discharge, and see how the two and visually see how the two interact with each other. So runoff occurs anywhere across the land over any surface, but river discharge is usually only happens in the river drainage network. And so in this regard, we need to filter the Oder river discharge dataset, so only the main arteries stand out in our plot. And this is why we are going to use a specialized upstream area dataset that will allow us to mask out the noise, so to say, and only display the main river arteries of the basin. And so to do this, so we have to retrieve the upstream area dataset. So it's actually associated with the global flood awareness system dataset that we have retrieved to this dataset, but I don't think it is retrievable through the WEkEO platform, which is why I've downloaded it directly from the Copernicus Climate Data Store. So you can see here the main variables that we have. Oh, maybe it's not the right one, this one. Daily statistics. Oh yes, sorry, it is. I didn't see the read more button. So remember, this is a dataset that have many variables, but our variable of interest is the total precipitation, which we should see somewhere in this dataset. It's in alphabetical order, so you can see how vast this is. So yes, this is our total precipitation variable that we had retrieved. And if we go to the bottom of the page, well, it's not here. Let me look for it. So to retrieve this upstream area dataset, so it is actually associated with the global flood awareness system data that we had just retrieved. But however, I don't think that this particular auxiliary dataset is retrievable through the WEkEO platform. So I suggest that I've actually downloaded this sample of the dataset directly from the Copernicus data store. So you can see here that it is the same dataset with the river discharge, runoff, etc. And so we can have access to some auxiliary data. So it's difficult to find, but here you can see that we have the related upstream area variable, and this is what we need. So I've retrieved it, and it is available in the data package that is provided with this tutorial. And so this dataset shows us for each pixel of the map of the GloFast data how much water flows into each pixel from the pixel surrounding the considered pixel. Yes, so yes, it's for each pixel it gives us the total area that contributes with water to this grid point. So of course the unit of each up area value will be in square meters, and so if we only keep pixels that have a very wide area that flows towards them, it will only give us a pixel that belong to the main arteries of the Oder river. And so we will use this dataset to filter the river discharge data that we had before. And so to show you this visually, I will just show you the river discharge dataset on a map with and without the upstream area filtering. I've just chosen this example on the 10th of September, but this is not really crucial which date that was. And so we can see that our raw river discharge dataset, we can sort of distinguish the biggest arteries of the outer river. But we can see that if we keep pixels that have 500 square kilometers contributing to their water content, we do have some more arteries appearing here. So, and this really highlights how the river network is built in this area. So this is like Czechia and Poland here, and the Oder River. So you can see that with this filtering, we have removed noise from the small streams and from the surface runoff from the river discharge dataset. And yes, as I've mentioned, this will allow us to highlight only the pixels belonging to the main river channels. And now we are ready to create the final animation. So as a reminder, the goal is to show how surface runoff and river discharge interact with one another. So our animation will look a lot like this. So in the background we have the surface runoff shown in orange, and the river discharge we will show in blue. And let's just see how this works. So we go from the 1st of September to the 10th of October to have a very wide and complete representation of the storm and of its aftermath. So we can reselect the data over this time period. Here is just a setup for the variables and constants to be visualized. So here's the threshold to filter the upstream area river discharge. Here are the minimum and maximum values to set up the color grading. Here we set up the animation, and here we display it. So it will take a few seconds, but it will appear. Alright, so our animation has appeared. So I'm just going to zoom out a little bit so we can see it completely. Yes. Just adjusting. Oh, perfect. And we can see that from the first days of September we have nothing much happening. So we have very light orange tones here that well, make for a very negligible surface runoff. But here, 14th of September, we can see that we have some stronger runoff happening here near those mountain range here in the south of Czechia. And here we have the very strong surface runoff in the south of the basin. And you can see that immediately afterwards we have the rivers here filling up with strong river discharge. And we can see that over the days, this discharge moves downstream towards the estuaries here, towards the sea. And this is a very compelling look of the response of the rivers to the storm. And we can see that after a while, the river discharge starts to decrease. We can see that the blue tones here become lighter and lighter over the days, and then we can just animate it automatically. And yes, for each big river here, the propagation is very obvious. So yes, as I've mentioned, we can clearly visualize the propagation as the runoff enters the drainage network. And yes, in the aftermath of this hydrological pulse, we can see that the river discharge is slowly decreasing and returning to normal. Probably with more days of data, we could see it come back to the state that it was in the beginning of September. Here it's still stronger in the beginning of October than before the storm. But yes, the main takeaway here is that we can clearly see the transition from peak crisis to and its propagation into the drainage system. So this was a very, very compelling look on the consequences of the Boris storm. And well, we are reaching the end of the notebook. So you can here are some ideas if you want to go deeper and analyze other similar events. So here are a few suggestions, but you can of course study any storm that you would be interested in. We've chosen those ones because they are analyzable using the same datasets that we've used for this tutorial. So there is the Burnt in Germany and Belgium in 2021, the Daniel storm in September 2023 in Greece. We also have some more older event from June 2013. So there are many possibilities to reproduce this analysis. So feel free to do this if you want to exercise more your Python knowledge that you have acquired through this notebook. So, okay, we are reaching the end of this notebook. So, as a reminder, we've analyzed the impact of the Boris storm using Python and Copernicus data. We've performed spatial temporal analysis. We've transformed SDF files into time series or into clear visualization of extreme rainfall, of flooding indicators. So, feel free to reuse this toolkit to make your own investigations. So thank you for your attention. I do hope that you enjoyed this tutorial, and see you next time. Goodbye.